Welcome to today's class. Today we shall deal with thermochemistry, part of thermodynamics. Under thermochemistry, we deal with heats of reactions and factors influencing the heats of the reactions and applications of Hess law. So mainly we will concentrate on the calculations of delta H and delta E. So what is heat of reaction? What is the heat of reaction? The amount of heat evolved during a chemical process when the reactants undergo complete transformation as given in the balanced chemical equation. As given in the balanced chemical equation. What are the factors that influence the heat of the reaction? 1. Temperature, 2. Mass, and 3. Conditions at which the chemical process is carried out. So if the process is carried out at a constant pressure, heat of reaction Q is equal to delta H. What is Q? The amount of heat evolved or absorbed during a chemical process. When the reaction is carried out at constant pressure, Q will be equal to delta H. When the reaction is carried out at constant volume, Q will be equal to delta E. What is the relation between delta H and delta E? Delta H is equal to delta E plus P delta V, or delta H is equal to delta E plus RT delta N. Now here what is the other important point to be remembered? Heat of formation of a compound will be equal to enthalpy of the compound. Why it is so? Because the enthalpies of the elements at standard conditions are taken as 0. Now what is when bond energies are given, what will be the heat of the reaction? Heat of the reaction will be equal to sum of bond energies of the reactants minus sum of bond energies of the products. When heat of combustion values are given, how do you write the heat of the reaction? Sum of the heat of combustion values of reactants minus heat of combustion values of the products. When heats of formations are given, how do you write heat of the reaction? Sum of the heats of enthalpies of the products minus enthalpies of the reactants. What is enthalpy? Enthalpy and heat of formation are one and the same. Now basically the numericals in thermochemistry are types of the heats of the reaction are applications of Hess law. What is Hess law? The net heat change in a chemical process remains the same whether the process is carried out in one step or in multiple steps. So let us discuss the concepts through the numericals. So first, what are the types of the heats of reactions? Heat of formation, heat of combustion, heat of neutralisation, heat of hydration, heat of solution. We will discuss those types of the heats of the reactions and the important points regarding the heats of the reactions through the numericals. Let us begin with the discussion through the question. Now what is given here? N2 plus 3H2 gives us 2NH3. Delta H is equal to minus 46 kilocalories. And what is the question? Heat of formation of ammonia. So how do you define heat of formation of ammonia? Heat of formation of ammonia means the amount of heat absorbed or evolved, or simply enthalpy change during the formation of 1 mole of ammonia from its elements. That is, what are the constituent elements? Nitrogen and hydrogen. But in the given problem, for 2 moles, during the formation of 2 moles, What is the amount of heat evolved? 46 kilocalories. 46 kilocalories. For 1 mole of ammonia, what will be the amount of heat evolved? Nothing but 23 kilocalories. 23 kilocalories. So minus 23 kilocalories. Because since the process is exothermic, delta H takes a negative sign. Next. Here also the same logic holds good in this problem also. What is the problem? What is the numerical given? During the formation of 4 moles of SO3, for 4 moles of SO3, for 4 moles of SO3, what is the amount of heat evolved? 1590 kilojoules. 1590 kilojoules. For 1 mole of SO3, for 1 mole of SO3, what will be the enthalpy change? 1590 by 4, approximately 397.5 kilojoules. So option 2 is the answer. Next. Now, what is the definition of the heat of combustion? This is a problem based on the heat of combustion. So we must be thorough with the definition part. What is the definition of the heat of combustion? The amount of heat evolved during the complete oxidation or during the complete combustion of 1 mole of the compound. 1 mole of the compound, that is due to the combustion of 1 gram molecular weight of the compound. That is the definition of the heat of combustion. Now what is the compound under consideration? Benzoic acid. Benzoic acid. What is its molecular weight? What is its molecular weight? 77 plus 12 plus 32 plus 1. So it must be 122. It must be 122. Now what is the given? 10 grams on burning. 10 grams on burning is producing 10 kilocalories. 10 kilocalories. 1 gram molecular weight. 1 gram molecular weight, that is 122 grams on burning, produce how much? 122 kilocalories. Heat of combustion values are always exothermic. Combustion reactions always proceed with evolution of energy. Therefore, delta H takes a negative sign only. Delta H takes a negative sign only. If the process is carried out in a closed vessel, then the volume will be kept constant. If the process is carried out in an open vessel, pressure will be kept constant. Next. Heat of combustion of ethylene is minus 337 kilocalories. If 5.6 liters of oxygen is used at STP in the combustion, what is the heat liberated? What is the general equation? General equation for the heat of combustion of the hydrocarbons, CXHY plus X plus Y by 4, X plus Y by 4 O2, X plus Y by 4 O2 gives us to XCO2 plus Y by 2 H2O. This is the general equation for the combustion of the hydrocarbons. For the combustion of the hydrocarbons. Suppose if the compounds contain carbon, hydrogen and oxygen, what will be the general equation? CXHY plus X plus Y by 4 minus Z by 2 O2 will give rise to XCO2 plus Y by 2 H2O. Now, what is the compound under consideration? What is the compound under consideration? Ethylene. In place of X we write 2. In place of Y we write 4. Then 2 plus 1, 3O2. 3O2 will give rise to 2CO2 and 2H2O. This is the equation. This is the equation. Now, what is the delta H value here? Minus 337 minus 337 kilocalories, minus 337 kilocalories. That is, when 1 mole of ethylene, 1 mole of ethylene is subjected to combustion in presence of 3 into 22.4 liters of oxygen, we get how much of the energy? 337 kilocalories. Now in the problem, what is given? 5.6 liters. When 5.6 liters of oxygen is used, what is the amount of heat evolved? 5.6 by 3 into 22.4 into 337. So 5.6 4 times 12, approximately it will be 26 or 28. So option is 1 will be evolved. This is a stoichiometric based problem. Next, human body requires 2370 kilocalories of energy daily. The heat of combustion of glucose is minus 790. That is 1 mole of glucose can give rise to 790 kilocalories on burning. What is the definition of heat of combustion of the glucose? The amount of heat evolved when 1 mole of glucose is subjected to the combustion. So 1 mole of glucose on combustion produces 790 kilocalories. 2370 kilocalories are given by how many moles? 2370 by 790, 3 moles of glucose. So what will be the mass of the, then what is the mass of the glucose? Mass of the glucose is equal to number of moles multiplied by molecular weight, 3 into 180, that is 540. That is 540 grams is required. Option 2 is the answer. Just stoichiometric based equation. 790 kilocalories is given by 1 mole, that is 180 grams. 2370 kilocalories which is required by the human body will be given by 3 moles of the glucose. What do you mean by 3 moles of the glucose? How much mass? It comes to 540 grams. Next question. The heats of combustion of ethane and acetylene are ethene and acetylene are minus 341.1 and minus 330, minus 310.9 kilocalories per mole respectively. What is the best fuel among them? So which gas can be considered a best fuel? The gas with high calorific value, will be the best fuel. How do you get calorific value? Calorific value is given by, mathematically calorific value is given by heat of combustion value by gram molecular weight. Heat of combustion by gram molecular weight. So higher the calorific value, better is the fuel. Now for ethane, what is the heat of combustion for ethane? For calorific value of ethane, what is the heat of combustion for it? Minus 341.1 by what is the molecular weight of ethane? 30. Next, ethylene. For ethylene, it must be ethylene. For ethylene, what is the heat of combustion value? Minus 330 by, for ethene means C2H4. What is the molecular weight? 28. And for acetylene, what is the What is the heat of combustion value? 310.9. 310.9. What is the molecular weight of acetylene? 26. If you simplify this, you will get the calorific value. So, which is giving the high calorific value from these values? Acetylene is giving the high calorific value. So, it is considered best fuel among the given set of the gases. Among the given set of the gases, which gas has a high calorific value? Acetylene. How do you calculate the calorific value? Heat of combustion value by gram molecular weight. Next question. The heat of combustion of benzene at 27 degrees centigrade is found by bomb calorimeter for the reaction is the heat evolved on burning 39 grams of benzene in open vessel. The first reaction pertains to the process carried out at constant volume, because in bomb calorimeter the vessel will be closed. So, the first delta H 780 kilocalories corresponds to delta E value, because volume is kept constant. Now, they want us when the vessel is open, implies that it is carried out at a constant pressure. Now, we have the delta H value with us, delta E value with us. First, we have to find the delta H. What is the delta E? Why it is taken as delta E? Because when the process is carried out in bomb calorimeter, the vessel will be closed. So, the heat of the reaction pertains to the heat of the reaction at a constant volume. So, delta E is equal to 780. And what is delta H? Delta H is equal to how much? What do you mean by delta H? Heat of the reaction at constant pressure. What is delta E? Heat of the reaction at constant volume. What is the relation between delta H and delta E? Delta H and delta E is equal to delta E plus RT delta N. RT delta N. What is delta E value? Minus 780. Minus 780. And what is RT delta N value? RT delta N value. What is in kilocalories? In kilocalories, R value is 2 into 10 to the power minus 3. 2 into 10 to the power minus 3. What is the temperature? 27 degrees centigrade, 300. What is the delta N value? What is the delta N value? Minus 3 by 2. Minus 3 by 2. Minus 3 by 2. Gets cancelled out. 900. 900.9 kilocalories. RT delta N is equal to minus 0.9 kilocalories. So, delta H will be equal to minus 780 minus 0.9 minus 780.9 kilocalories. What is delta H? What is it? Delta H, the enthalpy change during the burning of 1 mole, that is for 78 grams of benzene on burning is producing 780.9 kilocalories. 39 grams will give rise to how much? 390.45. 390.45 kilocalories. Option 3 is the answer. Next question. Here delta H, this is nothing but acid base neutralization reaction. Acid base, in case of acid base neutralization, take place between a strong acid versus a strong base. Between a strong acid versus a strong base, we can heat of the neutralization process take place in 2 steps. One, ionization of the acid and base. Second step is formation of the water due to the combination of H plus ions and OH minus ion. So, neutralization reactions take place in how many steps? 2 steps. First step is ionization of the acid and base to produce H plus ions and OH minus ion. And what is the second step? Combination of H plus ions and OH minus ions to form the 1 mole of the water. So Q will be equal to Q1 plus Q2. Q1 plus Q2. What is Q? Heat of neutralization. What is Q1? Heat of ionization. Q is equal to heat of neutralization value. Q1 is equal to heat of ionization. Heat of ionization of the acid or base. And what is Q2? Heat of formation. Heat of formation. Heat of formation of water. Heat of formation of water from H plus ions and OH minus ions. From H plus ions and OH minus ions. This value is always constant, which is equal to minus 13.7 kilocalories, or in terms of joules minus 57.3 kilojoules. So Q2 value is constant. Which are variable? Q and Q1 values are variable here. When neutralization take place between a strong acid and strong base, this Q1 value will be practically be 0. As a result, Q will be equal to Q2. This happens only in case of strong acid versus a strong base. Strong acid versus a strong base. So what is Q2? What is Q2? Heat of formation of water. Heat of formation of how many moles of water? 1 mole of water due to the combination of H plus ions and OH minus ions. Here how many moles of water are formed? 2 moles of water is formed. For 1 mole of water, what is the delta Q2 value? Minus 13.7 kilocalories or minus 57.3 kilocalories. Here 2 moles of water is formed. So what will be the value? 2 into minus 13.7, which is equal to minus 27.4 kilocalories. Option 3 is the answer. Next, these are the important points to be remembered during the heat of the neutralization. This is nothing but decomposition of the water. So here when the heat of formation is 13.7 kilocalories, heat of decomposition, heat of formation will have same values but opposite sign. If the heat of formation of the water is minus 13.7 kilocalories or minus 57.3 kilojoules, heat of dissociation of the water into H plus ions and OH minus ions is nothing but 57.3 kilojoules. Here it is not 2 moles are not getting dissociated, here only 1 mole, because 2H2O means H2O plus H2O giving rise to H3O plus and OH minus, means here what is H3O plus? Nothing but H plus and H2O. So in the process how many moles are getting dissociated? Only 1 mole is getting dissociated. So heat of the reaction will be 57.3 kilojoules only. Next, equal volumes of equimolar HCl and H2SO4 are separately neutralized by dilute NaOH. Then heat liberated is X kilocalories and Y kilocalories. What is the basic definition of the heat of neutralization? The amount of heat evolved when 1 gram equivalent weight of an acid is exactly neutralized in aqueous solution. Here equal volumes of equimolar HCl, their molarities are equal but their normalities are different. If the molarity of HCl is X, its normality is also X. If the molarity of HCl is 1, its normality is also will be equal to 1. But in case of H2SO4, if its molarity is equal to 1 and its normality will be equal to 2. its normality will be equal to 2. So, what is the point? When equimolar solutions of HCl and H2SO4 is neutralized, what is happening here? If X equivalents of HCl is neutralized, 2x equivalent of H2SO4 will be neutralized. Here in case of HCl, how many equivalents are getting neutralized? 1 equivalent. In case of H2SO4, how many equivalents get neutralized? 2 equivalents. So, ratio of equivalents getting neutralized is 1:2. If for heat liberated, for HCl is x kilocalories, heat liberated for H2SO4 will be 2x, that is implies 2x will be equal to y, 2x will be equal to y, or x will be equal to y by 2, or x will be equal to y by 2. Option 2. Once again, what is the point? The equimolar equal number of moles are getting neutralized, but in terms of the number of the equivalents, what is the ratio of the equivalents that are getting neutralized? 1:2. If it is x, it will be heat evolved will be for H2SO4 will be 2x, that is 2x is equal to y, x is equal to y by 2. Next problem. 50 cc of 1 normal KOH. Here, what is the number of equivalents that got neutralized? Number of equivalents of H2SO4. Number of equivalents of H2SO4 is equal to 0.2 into 50 by 1000. Number of equivalents of NaOH. Number of equivalents of NaOH. NaOH taken is equal to 50 into 1 by 1000. 50 into 1 by 1000. This is 10 by 1000. 10 by 1000. 10 by 1000. 10 by 1000. This is 50 by 1000. 50 by 1000. This is 1 into 10 to the power of minus 2 equivalents. This is 5 into 10 to the power of minus 2 equivalents. In this case, which happens to be the limiting reagent, sulfuric acid is the limiting reagent. So, amount of heat liberated depends upon the number of equivalents of H2SO4 neutralized. When one equivalent rate of H2SO4 gets neutralized, the amount of heat will be evolved either minus 13 point, in case of kilojoules, it will be 57.3 kilojoules. But here, how many equivalents got neutralized? 10 to the power of minus 2 equivalents got neutralized. Therefore, it will be 0.573 kilojoules or 573 joules. Or 573 joules. 570. Option is printed wrongly. It must be 573 joules. 573 joules. Next. The heats of neutralization of HCl with NH4OH and that of NaOH with CH3COH are respectively minus 51.4, minus 50.6. What is the heat of neutralization of acetic acid with NH4OH will be? So, for the first heat of neutralization of HCl with NH4OH, HCl with NH4OH, NH4OH, what is the equation? NH4Cl plus H2O. Here Q is equal to Q1 plus Q2, Q1 plus Q2, Q1 plus Q2, Q1 plus Q2 is equal to how much? Minus 51.4, minus 51.4 kilojoules. Therefore, what will be the Q1 value? What will be the Q1 value? Minus 51.4 minus of minus 57.3, that is equal to 5.9 minus 5.9 kilojoules. What is Q1 stands for here? Heat of ionization of the ammonium hydroxide. So from the first equation we have to get the heat of ionization of ammonium hydroxide. From the second equation, what is the second equation? CH3COOH plus NaOH, CH3COOH plus NaOH gives us to CH3COO plus H2O. So here also Q is equal to Q1 plus Q2. Q1 plus Q2 is equal to how much? Minus 50.6. Minus 50.6. Here Q1 is equal to how much? Minus 50.6 minus of minus 57.3. 57.3. Here it is 6.7. Here approximately it is equal to 6.7 kilojoules. What is Q1 here? Heat of ionization of acetic acid. Heat of ionization of acetic acid. Heat of ionization of acetic acid. Now coming to the third question, third equation, CH3COH plus NH4OH giving rise to CH3COO NH4 plus H2O. Here Q will be equal to Q1 plus Q2. What will be the Q1 value here? Heat up, because acetic acid and ammonium hydroxide both happen to be the weak. Q1 is equal to heat of ionization of acetic acid plus heat of ionization of ammonium hydroxide. What is the heat of ionization of ammonium hydroxide? 5.9. What is the heat of ionization of acetic acid? 6.7 kilojoules. 6.7 kilojoules plus what is Q2? Q2 is always constant. What is that? 57.3. What is the value? 6 plus 6.6, 12.6. When 12.6 is eliminated, subtracted, we get 44.7, 44.6 or 7, 44.6. The value is minus 44.6 kilojoules. So this is very important concept. It appears to be, the problem appears to be lengthy, but certainly it is not lengthy. Here heat of neutralization is always equal to Q1 plus Q2. What is Q2 stands for? Heat of formation of the water. Its value is always fixed. It is always its value is always fixed. So if the heat of neutralization is less than 57.3, implies that the difference in the heat evolved is nothing but heat of ionization of the weak component. So here we have to get from this value, we have to get the heat of ionization of ammonium hydroxide. And what is, how do you get it? Just simple. How do you get it? Q minus Q2. Q minus Q2. Here also heat of ionization of the acetic acid, Q minus Q2. Now here both happen to be the weak components. So we have to get the heat of ionization of acetic acid and ammonium hydroxide from the first two equations. How to get this? This Q minus Q2. Here also Q minus Q2 will give us. Next question. Heat liberated in the neutralization of 500 ml of 1 normal HCl and 500 ml of 1 normal NH4OH is 1.36 kilocalories. Here what is Q? What do you mean by heat of neutralization? The amount of heat evolved during the neutralization of 1 gram equivalent. Here number of gram equivalents neutralized is number of gram equivalents neutralized is equal to N into V by 1000, N into V by 1000, 500 into 1 by 1000, 500 into 1 by 1000, that is 0.5 equivalents, 0.5 equivalents, 0.5 equivalents. During the neutralization of 0.5 equivalents, how much energy is released? Minus 1.36. For 1 equivalent, what will be the amount of heat liberated? Minus 2.72 kilocalories. Now write the equation. Q is equal to Q1 plus Q2. Now what is the Q value? Minus 2.72 kilocalories, not minus 1.36. Why we cannot take minus 1.36? 1.36 kilocalories of heat is liberated due to the neutralization of 0.5 equivalents. So, but what is the definition of the heat of neutralization? Amount of heat evolved for the neutralization of 1 equivalent. So, during the neutralization of 1 equivalent, we get 2.72. That should be substituted in this expression, and we don't know the Q1 value. Q2 value is always constant, that is minus 13.7. So, Q1 will be equal to 13.7 minus 2.72. Approximately it will be 2.72, 11 kilocalories, 10.98, 10.98 kilocalories. So, option 1 is the answer. Always heat of neutralization equal to Q1 plus Q2. But what is Q? The amount of heat liberated during the neutralization. How many equivalents? 1 equivalent in the process. Next, in which of the following combinations of HCl and NaOH the heat energy liberated is maximum? In a process, this is nothing but application of limiting reagent. In a neutralization process, the amount of heat liberated always depends upon the number of equivalents of limiting reagent neutralized, because this is nothing but, this type of the problems are nothing but applications of the limiting reagent. Since just as in a stoichiometric equation, the amount of the product depends upon the quantity of the limiting reagent, here also the amount of heat liberated depends upon the number of equivalents of the limiting reagent neutralized. In the first option, what is the limiting reagent? HCl. What is the limiting reagent in the first option? HCl. How many milliequivalents are involved there? 1 milliequivalent of HCl gets neutralized. 1 milliequivalent of HCl gets neutralized. In the second option, what is the limiting reagent? NaOH is the limiting reagent. So, how many milliequivalents of NaOH got neutralized? 2 milliequivalents. How do you get milliequivalents? Number of molarity into normality into volume in ml. How many milliequivalents of NaOH got neutralized in the second option? 2 milliequivalents. Third one is how many milliequivalents got neutralized? 2.5 milliequivalents. 2.5 milliequivalents. In the fourth option, which is the limiting reagent? NaOH. How many milliequivalents got neutralized? 1.5 milliequivalents. In which case, number of milliequivalents neutralized, number of equivalents neutralized is more in the third option. So, in the third option, heat evolved will be more. Option 3 is the answer. This is the important point to be remembered. Next, under the same conditions of how many moles of 1 molar KOH and 0.5 molar H2SO4 solution respectively when mixed to give a total volume of 100 ml produce the highest rise in temperature. 1 molar KOH, 0.1 molar H2SO4 means 1 molar KOH means 1 normal KOH, 0.5 molar H2SO4 implies 0.5 molar H2SO4 implies 1 normal H2SO4. So this is also based on the quantity of the heat liberated depends upon the quantity of the limiting reagent. In the first option, which is the limiting reagent H2SO4, how many milliequivalents get neutralized? 33 in the first option. In the second option also, how many milliequivalents get neutralized? 33. And in the third option, how many milliequivalents get neutralized? 40. In the fourth option, how many milliequivalents get neutralized? 50 milliequivalents. In which case, number of milliequivalents neutralized are more in the option 4. Therefore, option 4 is the answer. How to get number of the milliequivalents? Volume multiplied by normality. In the first option, we have 67 is 1, 33 is another one. So, which is the limiting reagent? 33. So, 33 milliequivalents. Second option is also one is 33 ml, other one is 67 ml. How many milliequivalents get neutralized in this second option? 33. In the third option, 40 milliequivalents. In the fourth option, 50 milliequivalents get neutralized. So, amount of heat evolved will be more in the case of fourth option. So, fourth option is the answer. Next. Now, the point is rise in temperature is a maximum. How do you get rise in temperature? Q is equal to ms delta T. Q is equal to ms delta T. Rise in temperature delta T is equal to Q by ms. So, what is Q? Quantity of the heat liberated. What is Q? Quantity of the heat liberated. Quantity of the heat liberated always depends upon the quantity of the limiting reagent. That is why Q depends upon the quantity of the limiting reagent. Anyway, which can be limiting reagent? Either acid or base whose number of milliequivalents are less. NER, NBVB. And what is this MS? Mass multiplied by specific heat. This quantity depends upon is proportional to the volume of the mixture. This MS value is proportional to the volume of the mixture. This quantity of the heat liberated is proportional to the NAVA or NBVB, whichever is less, because I am not going to calculate the exact quantity of the heat liberated. We are trying to know the relative quantities, which process in which experiment more heat will be released. So, quantity of the heat depends upon the quantity of the acid or base, which are less quantity. It always depends upon the quantity of the limiting reagent. How to identify the limiting reagent? NAVA or NBVB, whichever is less. This is the easy way of identifying. There are two experiments conducted. Delta T1. 1 liter of 1 molar HCl is mixed with 1 liter of 1 molar NaOH. Then rise in the temperature was found to be T1. So delta T1 will be equal to 1 molar NaHCl and 1 molar NaOH. What will be the number of equivalents? 1 liter of 1 molar HCl, Q1. Q corresponds to how many equivalents got neutralized? 1 equivalent. What is the volume? 1 liter plus 1 liter. MS is proportional to 1 liter and 1 liter. And delta T2, in another experiment, 1 liter of 0.5 molar NaOH and 1 liter of 0.5 molar HCl. What is the rise in temperature? Delta T2. Here, how many milli equivalents got neutralized? 0.5. And this, what is the mass? Corresponds to 1 plus 1. 1 plus 1. 1 plus 1. So, from this, what is delta T2? What is delta T2? Delta T2 will be equal to delta T1 by 2, or T2 is equal to T1 by 2. T2 is equal to T1 by 2, or T1 is equal to 2T2. T1 is equal to 2T. Because here I am not exact, we are not calculating the exact magnitude of Q and MS. Just I am taking the relative values. What is the total quantity of the heat liberated? It is proportional to the heat liberated during the one equivalent weight. Here, what is the mass here? Here 2 liters mass is here. Here also 2 liters mass is there. So mass is getting cancelled out. Here rise in temperature is due to the neutralization of one equivalent. In the second case, rise in the quantity of the heat is due to the neutralization of 0.5 equivalents, in which case the quantity of the heat liberated is more in the first case. That is how we can get the answer. Even though it appears to be in a rough method, it is we can easily guess in which case rise in temperature is more. Next. So what is the enthalpy of ionization? What is the enthalpy of ionization? The amount of heat evolved, during the formation of 1 mole of the ions, from its constituent elements, in the aqueous solution, Now, and for arbitrarily we take enthalpy of ionization of H plus ion. Enthalpy of ionization of H plus ion will be taken as 0. Now, what is the required equation for the enthalpy of ionization of the OH minus ion? H2 plus of O2 gives H2, of O2 gives H2, excess of water gives H2, H plus OH minus, H plus OH minus. This is the required equation. How do you get this equation? How do you get this equation? How do you get this equation? Equation 1 minus equation 2. Equation 1 minus equation 2. Equation 1 minus the difference between the, it is equation 1 plus equation 2. How do you get this equation? Equation 1 plus equation 2 will give us this required equation. Equation 1 plus equation 2 will give us the required equation. Equation 3. So, delta H in the third equation is equal to delta H1 plus delta H2. What is the delta H1? Minus 286.2 and plus 57.3 is equal to minus 228.5. This is the required equation, and these are the given equations. By manipulating the given two equation, we must get this equation. How to get it? By adding the first two equations, we can get the third equation. Next. this is also the same procedure. This is also the same procedure. When you add the first two equations, you will get the second equation. So minus 92.4 and the minus 74.8 will give rise to the around minus 167.2. What is the required equation for the heat of ionization of the Cl minus of H2 plus of Cl2 gives rise to H plus and Cl minus. H plus and Cl minus. H plus and Cl minus. This is the required equation. How we can produce this equation from the given set, adding 1 and 2, adding 1 and 2. Delta H for the required equation is equal to delta H1 plus delta H2. This is a very important model problem, heat of ionization. How do you define heat of ionization? How do you define a heat of ionization? Nothing but amount of enthalpy change during the formation of 1 mole of the ions from their constituent elements in aqueous solutions. Next problem. So this water equivalent. So in this case 100 ml of water at 20 degrees centigrade and 100 ml of water at 40 degrees centigrade are mixed in a calorimeter until constant temperature is reached. Now the temperature of the mixture is 28 degrees centigrade. What is the water equivalent of the calorimeter? Here in this is a simple point. Heat lost by the hot water must be equal to heat gained by the cold water plus calorimeter. Heat gained by the calorimeter plus cold water. Now how do you get it? W1 means 100. How do you get heat lost or heat gained? MS delta T. Q is equal to heat gained or lost is equal to MS delta T. What is the M? 100 ml of the water. So we will take M as 1. For water, S value is 1. So what is the dt value? 40 minus 28. Now here, so water equivalent of the calorimeter is given by W, that is MS value for the calorimeter. And what is the mass of the cold water? 100. And what is the difference in the temperature? 28 minus 20. So W is equal to 100 into 12 by 8 minus 100. So 1200 minus 800, 400 by 80. So W must be around 50 kilos. 50 joules. It must be 50 joules. Option 1 is the answer. This is the question. In this we get water equivalent 50 calories, because since we have taken specific as of water as 1, it is 50 calories. If we convert into joules, 50 into 4.18, that is 209 joules. Option 4 is the answer. If If it is calories, it is 50. If it is converted into joules, it is 209 joules. Next, the dissociation energy of for CH4 is 400 kilocalories. In CH4, when CH4 dissociates, we get carbon plus 4 hydrogens. So it is 400 kilocalories. Delta H is equal to 400 kilocalories. From this, what is the average CH bond energy? Average CH bond energy is 400 by 4, 100 kilocalories. 100 kilocalories. Now in C2H6, C2H6 contains 6 CH bonds. 6 CH bond. What is the dissociation energy for C2H6? 6 into CH plus 1 into CC is equal to how much? 670. Now what is the energy of the 6 into CH means 6 into 100 plus 1 into CC, C bond energy is equal to 670. CC bond energy is approximately equal to 70 kilocalories. It is option 2 is the answer. From methane we got the CH bond energy. That value is substituted in the dissociation energy of ethane. Next, the heat of atomization of pH3 is 228 kilocalories. pH3 dissociation is delta H is equal to 228 kilocalories. So what is the average pH bond energy? Average pH bond energy in pH3, how many types of bonds? 3 pH bonds. For dissociating 3 pH bonds, what is the energy required? 228 kilocalories. Average pH bond energy will be equal to 228 by 3. 228 by 3, it will be 76. It will be 76 kilocalories. Now coming to the P2H4. In P2H4, we have 4 pH bonds. P2H4 we have 4 pH bonds. 4 pH bonds. 4 pH bonds plus 1 PP bond is equal to how much? 355. So 4 into 76 plus 1 PP bond is equal to 355. So 304. What is the PP bond energy? 355 minus 304 is equal to 51 kilocalories. 51 kilocalories. Next. Thank you very much. We will continue in the next class.